Hi, in this video, we want to take a look at how we can use clustering. And we're specifically going to go over an example with using clustering from Gower's distance. All right, so I would say there are 5 major reasons why we would be going through clustering. So the first 2 are inference. First one is I want to see a taxonomy of how our observations are similar to each other. Second one is that we believe that there are subgroups in our data, but the record of which observation goes to which subgroup was lost, wasn't recorded. We don't know what it is. I want to use data to try and find what are those subgroups. Another one is going to be anomaly detection or outlier detection. Now, when we do outlier detection, if I talk about like univariate, we just look at the largest or minimum values, and that gives us a pretty good idea. But when I have multivariate problems, I have multiple dimensions of data going, I really need to have something that can handle the multivariate structure. And my opinion is that single linkage clustering does a pretty good job with this. Another one that we would want to do is segmentation. So what I want to do, I want to break up my data into subgroups based off of, and I want those subgroups to be similar to each other. Now, why would we do this? Well, let's say I'm doing a modeling, I'm doing some predictive modeling, and I feel like regions of my data in a multivariate sense would perform better with different algorithms. Well, what do I want to do? I want similar groups of data put together, so that way when I do my fitting of my models, the model gets tuned to that subgroup very well instead of trying to tune to the entire data set as a whole. Another one will be feature engineering. So in this case, what we're doing, we take the clustering, we take the labels of the clusters, and then we use the labels as a predictor variable in supervised learning. So now something that's very important, very, very important about clustering is that this is an unsupervised learning technique. If I'm trying to do this feature engineering thing, realize that this is a component that I add on to other predictor variables. I do not just go, under normal circumstances, we don't just go using clustering for prediction. We don't use it for supervised learning problems because it's not tuned that way. That's not how it's going through. We do not include target variables in our clustering. We use only the predictor variables. All right, so now let's go ahead and go through an example using Gower's distance. Okay, so I'm going to take the CARS data set from UC Irvine's data repository. Here is the website for it. And we have a mixture of integer and ordinal data on this. And something I did, since the classification is our target variable, I went ahead and tacked that on with row names to be our the overall row names. That way, if I was to like start digging through, it'd be easier for me to find things, figure out what's going on. Now, when I load the data, I've got categorical data coming in, ordinal actually, and as it comes in, it's being interpreted as a character string. So what I want to do is I need to put it in the correct order. Now, if I leave default order, R will go ahead and go through and assume that alphabetical order is the correct one. It's not the case. So I go ahead and all of this code is just going through and putting the columns in the correct order. Now, something that I went ahead and did is I sorted the data by each column, and you'll notice that the target variable is on the far right. And so I do this on some problems so that as I look through my data, if I'm new to my data, if I've never seen it before, I can get a better feel of how certain levels connect and certain variables connect with the target variable. And so here we can kind of get an idea of what's going on. So we can see that, with persons, more, a lot more, and lug boot of big and safety of high, and also doors being 5 or more, was consistent with, or had correspond to a lot of very goods. Now, if I look up here, I can see 2 doors, 2 person, lug boot, safety low. You know, these values were going along with unacceptable. So this may be true overall, maybe not. You know, we notice that it's, you know, pretty well sorted for the more right columns, but at least I have like a direction to start digging into and start looking. All right, now if you're going to be doing Gower's distance in R, one way to implement this is to use the cluster package DAISY. All right, so here this just gives us a distance matrix. And I want you to notice that when I call the DAISY function, I do not include class in the data. I'm only using the predictor variables if I have a supervised learning problem. If I don't have a supervised learning problem, then I include everything that makes sense. Like I would not include ID variables. I would not include redundant variables. Now, before I do this, if I have numeric data, I would want to rescale my data more than likely. If I'm doing clustering, if I'm doing this, you know, if I'm going through this process, standard deviation tends to of a column tends to be proportional to the amount of influence that that column has in the overall output. And so if I want to make sure that each column has about equal influence, I need to go ahead and rescale the data. Here, I'm dealing with mostly ordinal data. I've got doors and persons are numeric. I'm going to go ahead and treat those as ordinal because doors are not all the same. You know, so you know, if you think about a van door on the side and you think about a sports car, 2-door, 2-seater, their doors are very different. And so even though we count them that way, I'm going to go ahead and put doors as ordinal, and then persons once again because of the seats. So if you think about, let's say, a three seats on like an old Chevy pickup, where you've got someone sitting that's straddling the gear shifter, then that is 3 seats, but it's not a full seat. So there's inconsistencies on like how much of a seat is a seat. So I will go ahead and include persons as categorical, as ordinal. All right, so now next thing I'm going to do, I'm going to run through and I'm going to go ahead and I'm going to build a bunch of hierarchical clustering models. Now, there are 2 steps in doing hierarchical clustering. Get the distance matrix, do the hierarchical taxonomy tree. Okay, 2 steps. So I have to make 2 choices. I have to choose a method here, choose a method here. My data is ordinal, so more than likely I'm going to be going with Gower's distance. So that really is, I don't have a choice there. That one's taken care of. Here I have a lot of different options. Now, when we do this, the distance matrix is almost always the part that takes the longest to compute. So if I need to, if I have deadlines, if computation time is an issue, then I would really only do like 1 distance matrix and then explore a few different clusterings. My favorites, my preferred ones are Ward D, complete, and single. And I roughly ordered these in a manner that kind of makes sense on certain properties on how well they give you even-ish groups. So single linkage tends to give you like observations by themselves in their own cluster, while Ward D does probably the best job overall of giving you approximately equal cluster size. And now this code is just to go through and give me the hierarchical clustering. All right, so let's talk about our first use of Gower's distance and hierarchical clustering. Let's say that I want a taxonomy on my observations. So when I say taxonomy, I want to know like which observations are similar to each other. And I want like a tree diagram to visually indicate the similarity between the observations. My opinion is that complete linkage is the best overall method for taxonomy inferences. Now, there are over 1,000 observations in the data set, and you can see that the row names are all on top of each other because I have so many observations. These trees, you really want to keep it down to about like 60, like at most 60, to be able to really see like on the print. Now, if you have a larger data set, what you can do is I could do the clustering, and then I could break up into smaller groups using the Q-tree function, and then redo the same algorithm on the subset. Or another thing that I've done is I've actually taken these plots on a really big size PNG file or PDF, make it really, really big. I go through and I plot on a PNG that's like this, that if I printed it up, it would be the size of a building. And then I zoom in to the parts I'm interested in. And I've had success doing that. All right, so here, this clustering is for Ward D. And notice that if I was to cut this into two groups, this group over here and this group over here. So each stem at the very bottom of the tree corresponds to an observation. And each observation comes together with other observations and goes up the tree like that. So here, if I was to say there were two groups, I would cut here. Everything that's to the left of this point would be in a group. Everything that's to the right of this point would be in a group. Now, next one is Ward D squared. So Ward D works to minimize standard deviation. Ward D squared works to minimize variance. Usually you get pretty similar results. There's just a difference in the height is probably the main difference between the two. I tend to use Ward D because standard deviation is on the same scale as the data. Now this one is average linkage. So here, this is looking at the average distance between points before the two clusters come together. Here's McQuitty. Here's complete linkage. Complete linkage works to make sure that the maximum distance between observations in two combining clusters is, it uses the maximum space, the maximum distance between the observations in the two clusters there before they come together. It's very, this one, it works to make sure that you don't have anything together that shouldn't be. It's a very strong, kind of extreme criteria, honestly. A lot of people like it. A lot of biologists I've talked to prefer this version. Now, the tree looks messed up on this one. This is how it came out of R. Here's median. Here's centroid. I believe this one's single. This one is single linkage. Single linkage does a good job for outlier detection. You really can't tell here, but frequently if I have single linkage, I'll have outlier observations by themselves in their own like section of the tree. All right, the next thing that we would possibly want to use clustering for is finding subpopulations. So in this situation, I believe that there are subpopulations of my data, but I don't know what they are. Like that column was dropped, it wasn't recorded. Maybe we didn't know about the subpopulation when we started recording data, and as we went through, we're like, oh, whoa, we missed something. Okay, so here, you know, what we want to do, we want to build that tree, and then we're going to cut that tree in a manner that will give us the groupings that we like. All right, so in this example, I'm going to go through and I'm going to use complete linkage. So I already built the model. So I'm going to use the Q-tree function to cut the data or partition the data into 4 groups. Okay, so this is my complete linkage tree. What I'm going to do is like I'm cutting into 4 groups by slicing here, and all of the observations that if I go down the tree and end up part of this group, this is one group. This would probably group 4. over here will be group 3. All the observations over here are in group 3. All these observations are in group 2. All these observations are in group 1. And so then this is kind of like I'm estimating what are the subpopulations. Now, after I do this, I have to go, I have to look, and I have to see what are these subgroups. Can I figure out like what is the common aspect to each of these? And so what I chose to do in this example was I tried to find kind of like a prototype vehicle for each of these groups. Okay, so as I look through, so my first group, we see that they have low, low, too, small, medium, unacceptable. All right, the vast majority of the data is unacceptable. So that's not going to really be that interesting. Also, that class was not included in the clustering. Safety is medium, lug boot is small, too, low, low. All right, so as I look through this, the feel that I get is that really the data is kind of like for complete linkage, in a lot of ways is grouping by doors and persons. And now, does that make sense for the subject matter? Well, yeah, that would, you know, doors and persons would correspond very well to the size and utility of a vehicle. So we have like, you know, 2 doors, 2 persons, so probably a sports car. 2 doors, 4 persons, so that would be, you know, a lot of like, you know, cars for, you know, smaller families or individuals. You know, that would also include like Mustangs and, you know, Mustangs, then Challengers and Camaros. 4 doors, 2 persons, so probably a utility vehicle. And then 5 or more doors, and more persons. So this is going to be probably like minivans and bigger vehicles. All right, the next thing we want to consider is outlier detection. Okay, so the big idea here is if I run through, I do clustering, and I have an observation that's out by itself in its own cluster, then that observation is probably an outlier. And so I want to take a look. Now, if I'm doing something with univariate data, I could go through and find outliers on the univariate aspect by just looking at the extremes. But if I'm multivariate, it's more complicated. I want to simultaneously consider all the variables at the same time. Clustering does a good job for this. Okay, so I played around with it. This one, I had to tinker with the model, figure out which one to go with. Single linkage, in my opinion, is the best overall method for outlier detection. Now, I had to play around with the number of clusters on this one, and I concluded that 30 was a good one for this problem. And so here, I'm just grabbing one observation that was off in its own cluster, and then I take a look. All right, so this one, it's the price is high, then the maintenance cost is going to be high. There's 5 or more doors, and it's got a lot of people. It's got a big lug boot, and it's high on the safety rating. So here, you know, this is going to be like a vehicle that, you know, 5 or more doors, a lot of people. It is probably going to be a distinct vehicle in and of itself. Now, next one is going to be segmentation. All right, so an example of why we would want to do segmentation or partitioning our observations is, let's say that I have different personnel taking on my client load. Well, what I would like to do is I would like to group my clients into similar groups using data, and then have an employee handle those clients. That way they're more specialized in what they're doing. If I put all of my similar clients together, the employee can kind of get like more experience on handling those clients themselves. So this is a way to do customer segmentation based off of data. Now, another reason why I would want to do this is if I want to handle my data differently depending on by groups. So I want to group my data into similar subgroups and then apply something in a different way. So let's say I'm doing supervised learning. And I believe that I've got, let's say, 4 subgroups of data when I look at my principal component analysis plot. Well, if I've got 4 subgroups, maybe I should have a different model for each of these subgroups. I want the best model that will work on my data. And so I would group my data into 4 different groups, and then I would use the best supervised learning model I could on each of the 4, instead of trying to fit one big model to the whole thing. My opinion is that Ward's D does the best job for this. And so here, I run through, I use Q-tree once again, and I just kind of picked 4 on this one. 4 was enough to be interesting. And so here, we can see that we have a different number of observation in each group. Ward's D does probably the best job of giving us even groups, but it's not a perfect job because it's concerned with standard deviation, not cluster size. Now, the next one is one that is all over the internet of people messing up clustering. They miss the point of what they're actually trying to do. It's very common on looking at the internet, looking at data blog posts, that people want to use clustering as a predictive modeling technique. It is not a predictive modeling technique. All right, when you do this, when you do clustering, you do not consider your target variable. Therefore, your algorithm does not tune to the target variable. Now, it might work out by happenstance that clustering will give you a good vector for the purpose of feature engineering, but that's a maybe, maybe not. It is not tuning to your target variable. So I want you to keep that forefront in your mind. That is number one most important thing. All right, the next thing I want to point out is that in a lot of clustering algorithms, the labels are coded as integer values. So you notice that we had 1, 2, 3, 4 previously in this video. Well, that 1, 2, 3, 4, if I took it as is, it would be taken to be a numeric vector, not a label, not a categorical data, not a character string. So if I was to attempt to use this vector for the purpose of feature engineering and I did not convert it to a character, then what would end up happening is that the model would work to fit it in terms of it being numeric, and that doesn't make sense based off the original data. So something that's very important is you notice I have the as character step right there. So I'm taking the clustering from Ward D that we already got. I'm converting it to a character because when I do my supervised learning, I want to make sure it knows that this is not 1, 2, 3, and 4. This is not numeric data. And so I went ahead and to kind of judge this as a technique for feature engineering, I went ahead and made a table. Now, if I look at this off of my table, I can see that 1, 2, and 3 have virtually always are unacceptable. And then cluster 4 has a mixture. All right, so now there are a few in 2 that are acceptable, but you can see that proportionally, virtually all of them are unacceptable in 1, 2, and 3. So what I could do is with this clustering, I could use like just if it's in cluster 4 or not cluster 4, I can make a binary vector, and then if it's not in cluster 4, then I would be prone to saying it's an unacceptable vehicle. If it is in cluster 4, then I need to go deeper into it. So this would work very well if I was doing something like random forest or a tree-based model. And here is a plot just to kind of give you a feel. So you can see that there's virtually all purple in 1, 2, and 3. There's a little bit of blue in 2. So in 4, it's possible that it's good or very good. It's still proportionally low, but we can see that the vast majority of vehicles that would be worth purchasing are in cluster 4. So I could use the clustering vector as a predictor variable in supervised learning. Just make sure that you have it as a character or binary. Now, on this step, if you don't know how many clusters to go with, anytime that you're clustering, if you don't know how many to go with, go low. Personally, I usually go with 2. I find that if I've never had experience of overfitting. It's rather conservative. I usually use clustering with just 2 unless I have a good reason otherwise. All right, well, that's all I've got for you. Take care and goodbye.